All right, welcome again, everybody. And today we are really pleased to have Keri Sather Wagstaff to tell us about Codeword ideals. Keri, please.
Great. Thanks, Christine. Thanks to everybody for coming. So for those of you who haven't engaged with me in the last couple of years, I'm Keri Sather Wagstaff. I go by Keri Ann. My pronouns are she, her. I am technically a faculty member at Clemson University, but I'm on leave to the National Science Foundation and I'm not involved in mathematics there, actually working on other things. The stuff that I want to talk to you about today is joint work with Felice Manganiello, who's a faculty member at Clemson University, and Joseph Skelton, who's a postdoc there and is on the job market. Hello. All right, so first a little acknowledgement of thanks. So I'm grateful to the organizers for agreeing to an alternative time. And the point for that was to allow me and others to participate without sacrificing time with family. And just to satisfy my curiosity, feel free to add a note in the chat if the time change made it easier or possible for you to attend today. So I'll have the talk is broken up into 5 parts. So as we'll see in a second, this talk is about the interactions between coding theory and information theory and combinatorial commutative algebra. So we'll talk about codes and ideals. And then there's going to be sort of we'll go back and forth between ideas in coding theory and ideas in combinatorial commutative algebra. And the properties in commutative algebra that I'll be interested in are prime decomposition and curl dimension of these monomial ideals that come up, niceness conditions like Cohen-Macauliness and Gorensteinness, and then part 4 will be about symbolic powers, which is a treat for me. Those of you who have known me for a long time, like Claudia and some others, remember back my dissertation was actually on symbolic powers. And so it's fun to come full circle with that. And then we'll wrap up. So as I mentioned, this talk will be, and I want to encourage folks, feel free to just unmute or raise your hand. And I'll depend on the moderators to take care of the chat for me. So I'm looking at the interactions between 2 fields of mathematics. One is coding and information theory, and this is where Felice comes in. So he's thinking about linear codes over a finite field, F, which is the field with Q elements, where Q is a prime power. And this is roughly an area of applied linear algebra. And then on the other side is where Joseph and I come in, which is on the algebra side, where we're interested in looking at square-free monomial ideals in a polynomial ring that I'll typically write as S over that finite field F, although the finiteness will only be relevant in a few places, and N variables where N will get used for a number of things throughout the talk, but they're always the same. And I like to have my talks with take-home points that you could walk away with, besides the theorems and such. And one is one that hopefully everybody here knows, which is combinatorial commutative algebra gives strategies for using algebra to interface with other areas. So really thinking of this as applied algebra, or some folks like applied algebraic geometry. So foundations of coding theory and information theory, I'm not going to assume that you know anything about those. So a linear code over our finite field F, an F linear code of length n and dimension k is a k-dimensional subspace of that finite field raised to the n, right? So I'm looking at vectors of length n whose entries are coming from that finite field F. And then K is going to be the vector space dimension of that subspace. And the elements of C are called the codewords of C. And let's see if I can do this. So I'm going to consider a fixed example for most of the talk, working over the binary field F2 with a code of length 3 and dimension 2. And that is the one that is spanned by these 2 vectors. So some things to note about the way I'm writing my vectors. I'm being as lazy as humanly possible, right? And so I'm not writing parentheses and commas, and I'm not writing column vectors. This is a convention that the coding theorists and the information theorists like. And of course, this code having two linearly independent spanning vectors over F2 has 4 elements. Got the trivial element 1, 1, 0, 1, 0, 1, my basis vectors, and then their sum 0, 1, 1. Okay. And although that example is about as trivial as it gets, while being not completely trivial, it will have some surprises at the end and some behavior that surprised us a bit from the algebraic side. In the binary case, the code word ideal of our linear code that we're carrying around is really easy to describe. I'm literally just going to take the square-free monomial ideal in my polynomial ring, where the number of variables is the same as the length of my code. And that's the monomial ideal that's generated by the non-zero code words. So I'm going to look at the x sub c's inside of S such that C ranges through all of the non-zero code words. And here, just to be absolutely clear, if my code word is written as a string of zeros and ones, then that corresponding monomial is just the product of the variables that actually occur with a 1 instead of a 0. So it's the product over the ci not equal to 0 of the x sub i's. And I'm writing it as non-zero instead of equal to 1 for a reason that'll become clear in just a second. So in our toy example, where that is spanned by these two vectors, but then has these 4 code words, right? Notice that my definition says I need to look at all of the non-zero code words, not just the basis vectors. And so that will give me 3 code words. The first one gives me, right, so the product of the first 2 variables, which I'll have as x, y, then the product of the first and third variables, which I'll have x and z, and then lastly, yz. And so that's in my f2, x, y, z, right? So for instance, notice that those 3 generators are irredundant. So we really do need to use all of the generators that come from all of the code words in there. In the non-binary case, and I forgot to mention, right, this definition is due to Oxley from 2011, as best I can tell, although Oxley doesn't use this term code word ideal. They're thinking in terms of other things that we'll get to in a little bit. So in the non-binary case, so where I'm looking at a field that's not just the elements 0 and 1, right, and this happens in coding theory and cryptography all the time, right? So then my code words can have other entries in them besides 0 and 1. I still look at certain square-free monomial ideals, but instead of somehow using those entries as distinct, yeah, so we'll just use the support of each of the non-zero code words. And the support is, just like in module theory, it's the place where your code word is non-zero. So just like on the previous slide, I'm taking the product of the variables that correspond to the non-zero entries of the code, right? Just doing it now over maybe it's F3 or it's F8 or something like that. Now what happens is we'll find that in this situation, the generators can be redundant, right? So for instance, so if I look over F3, the code that's spanned by those 2 linearly independent code words, I end up with a 2-dimensional code again over F3. So it's got 9 distinct elements. This code word will again give me the variables, the monomial xy. This one also gives me the variable xy because again, it's non-zero just in that first and second slot. The next two give me the same xz generator. These two give me the yz generator. And then these two give me xyz, which is extra redundant. So we get the same three generators for this code, even though now the generators are not necessarily unique. Okay. So this is the combinatorial commutative algebra object that I'm interested in the properties of. And that's what we're going to look at next. So in the back and forth between coding theory and algebra, we'll go back to the coding theory and we'll talk about generator matrices for linear codes. So for the rest of the talk, now I'm going to fix a k-dimensional code of length n over my finite field f, and I'm going to consider what's called a generator matrix for that code. And that's very simply a k by n matrix whose rows consist of generators for my code. Because the dimension is k and the length is n, those rows will actually form a basis for my code, right? So this is a matrix that's encoding a list of generators for my code. So for instance, in my toy example, in the binary case, I can use those two code words in order to give a generator matrix. Or, I could permute the rows or do any row operation because that won't affect the generator matrix property. And so I could have 1, 1, 0, 0, 0, 0, 1, 1, and so on. And there are 6 distinct generator matrices for this particular toy code. Now here's where we get into the area of information theory, right? So information theory, codes are generally, we look for our linear codes to be error correcting. And so there's redundancy built into them in order to account for the fact that we will have noisy channels and we'll lose information as we transmit our information. So an information set is a list of the columns of the generator matrix that span the column space. And I'll do my toy example at the bottom. The idea is these are the entries in my codes that guarantee that I can fully recover any code word, right? So as long as I know for certain the entries in these spots, then I can actually recover all of the entries. Right, so that's why this is an information theoretic notion instead of simply a linear algebra notion. Right, so let me jump down to my toy example before I get to the bullets here. So I'm looking at in my toy example for columns that span the column space, right? So this matrix has rank 2, and so I'm looking at all the pairs of linearly independent columns in my matrix. So for instance, the first 2 columns are linearly independent. So columns 1 and 2 form an information set for me. Similarly, columns 1 and 3 and columns 2 and 3 form information sets. And then I don't necessarily ask that they're linearly independent. So the full list of columns is also technically an information set, although as you can imagine, for lots of reasons, we'll want to focus on the minimal information sets. What may or may not be obvious, so the fact that this matrix G, my generator matrix, has full rank tells me, in fact, that the information sets are independent of the choice of generator matrix, right? So we'll talk about the information sets for the code instead of for a particular generator matrix. As we saw, this larger information set contains the other minimal ones. This is coming from the fact that the set of information sets is closed under supersets. And then the minimal ones I'll call are the ones that are minimal with respect to containment. Those correspond to the bases of the column space consisting of columns from the matrix. And so in particular, they all have the same size, namely the rank of, or the dimension of the code, right? The rank of the matrix. And this number K and its code number N will be coming up as we see the algebraic side of things in a little bit. So here's the algebraic side. I'm going to use the information that we've seen so far in order to write down the minimal prime decomposition of my code word ideal. And it's exactly obtained by taking the intersection of all the prime ideals that are generated by the minimal information sets. Right? So if you start with your code, take a generator matrix, find all the minimal information sets, those will exactly determine the prime ideals in the prime decomposition, or your minimal primary decomposition, if you like, of that square-free monomial ideal K of C, right? So I immediately get algebraic information that this ideal is unmixed of height K, because all of my minimal information sets have the same size, namely the rank of the generator matrix. And the curl dimension can be read off as the code dimension, right? So n minus k there. And so the take-home point here is that you take that code, use it to build a monomial ideal, you can read algebraic information straight off of the code, right? Which is a situation that I like. Really, I'm interested in getting information about my ideal from this other object, the code. In our toy example, there's a million different ways to think about this ideal. I like to think of it as the edge ideal of a 3-cycle, if you like. Or if you like, it's the Stanley Reisner ideal of 3 distinct points. And so the prime decomposition is easy to write down. This one happens to be self-dual, which leads to no end of confusion. But there's the prime decomposition for that one, right? And that exactly corresponds to those 3 minimal information sets. Is it right here? Yes. So there's minimal information set 1, 2, which corresponds to the first prime ideal in the decomposition, and so on for the minimal information set 1, 3, and 2, 3. One of the reasons why I'm particularly keen on combinatorial commutative algebra is because I love working with undergraduate students, and those of you who know what I was doing before with derived categories and all that sort of stuff, is very hard to do undergraduate research with students on that topic. And I got really, really frustrated with that. And so I like this particular topic and topics in graph theory in general, for instance, because I can talk to high school students about graph theory, right? I can talk to undergraduate students who have had a course in linear algebra about codes and generator matrices and stuff. And so I can get them thinking about questions of what these decompositions look like, even though they might not know that that's what I'm asking them about, right? I'm asking them about questions about bases of a column space. And then I start to talk to them about commutative algebra if they've had a course in modern algebra, and sort of rope them in. So now back to I'll call this commutative algebra side, although I recognize that this is a combinatorial side of things. And I'll follow Adam's lead last time of what we're going to assume students in a first course in commutative algebra have seen. And so I'll not assume simplicial complexes, although I'm fairly certain everyone here knows this. So a simplicial complex on vertex set V, which is the list of variables that I've been carrying around, is simply a non-empty subset of the power set. So I'm looking at a set of subsets of that vertex set that's non-empty and closed under subsets. Right. The elements of my simplicial complex, I'll call its faces. Since it's closed under taking subsets, the maximal elements with respect to containment are called the facets, excuse me, and the simplicial complex is called pure if every facet has the same size. And I'm really, yeah, I'm keen on understanding purity in a lot of different contexts, and this will be one of them. A little bit of notation that I'll want is for the simplicial complex generated by a list of subsets. So that is the smallest simplicial complex on that vertex set that has those faces, right? So it's the intersection of all the simplicial complexes that contain those faces, or if you like, it's the set of all F's in V such that F is contained in Fi for some I. Or if you like, it's the union of the power sets of those given faces there. I'm not assuming that those faces are incomparable, so these aren't necessarily the facets, but they will be in practice. A couple of simplicial complex examples. I'll typically draw these instead of writing out all the faces. So here's one that consists of three shaded triangles that are glued together. It has three facets, which I'll again write as code words. Right? Noticing that I'm suppressing the variables and just writing out the numbers for these, and I'm really thinking about these as monomials, for instance, in those variables. There are, of course, other faces, which include some of the edges, the vertices, and then also the empty face, which is always in there because I am non-empty and it's closed under subsets. This one happens to be pure because the facets all consist of three vertices, so they have dimension 2. A non-pure one, for some reason we don't use the word impure, which is fine. Would be something like this, where I have two shaded triangles and then one edge hanging off, right? So this facet uses only 2 of the vertices, whereas this facet uses 3 of the vertices. So that one's not pure. And why am I interested in purity? For a lot of reasons. I feel like I skipped something. Oh well, because I'm interested in co-Macauliness. There, I said it. Before I get to that, I want to talk about what it means for a pure simplicial complex to be shellable. So a shellable simplicial complex is one that's pure. And I know that there's a notion of shellability that doesn't assume purity, and I'm not thinking about that one today. So a simplicial complex is shellable if it has a shelling, and that is an ordering of the facets so that delta is gotten by gluing the FIs together in a nice way in sequence, right? And what we mean by gluing them together nicely is that if I take the simplicial complex that's generated by the first I many facets in the order that I've been given, intersect it with this simplicial complex, then I want that intersection, which is a simplicial complex again, to be generated by a non-empty set of maximal proper faces of this face here, right? So what do I mean by that in our example here? So I'm going to look at this. This is a shellable simplicial complex where this will be my F1, this will be my F2, and this will be my F3, because when I look at the simplicial complex generated by this one intersected with the simplicial complex generated by this one, that has its facets just this single edge, which is a maximal proper face of this triangle, my F2. At the next stage, I would look at the simplicial complex that's spanned by these two triangles, intersect with the simplicial complex that's spanned by this shaded triangle, which again is generated by that edge, that maximal proper face of my F3 triangle. If I were to switch the order of F1 and F2, I would no longer have a shelling, because, or sorry, F2 and F3. So if I start with this one and then try and move to this one next, then the intersection is this single vertex, which is not a maximal proper face of F3, right? So a simplicial complex can be shellable with some orderings being shellings and other orderings not being shellings. Okay, so we have to be careful about that. On the other hand, there are multiple shellings of this one particular. If I started with F2, then any combination of F1 and F3 would be fine. Using that non-shelling, one can easily find a pure simplicial complex that's not shellable, which is this one, because no matter what order you do things in, the intersection will always be this vertex, which is not maximal proper face of one of the triangles. Shellability is a concept that it grows on you once you see what it can do. I didn't get it at first, and so I like to sort of say the point to me is that shellability is good for arguments, for induction arguments. Specifically on arguments where you want to induct on the number of facets of a simplicial complex, and you want to use short exact sequences to give long exact sequence arguments, right? So you can use this subsimplicial complex and this subsimplicial complex to build a short exact sequence. We've controlled the intersection here, which is controlling the third piece of the short exact sequence, which is giving me control over certain aspects of the long exact sequence. Okay, and that's really the way that I think of shelling in the big picture. Before I get to the consequences of shellability, I want to talk about an example of some simplicial complexes that are becoming favorites for me. And these I'm going to be a little bit sloppy with the language and call these representable matroids. I'm going to fix a k by n matrix in my field F. And I'm going to point out that every subset of a linearly independent set of columns is linearly independent, right? And so that says that if I look at the set of linearly independent columns of G, then that forms a simplicial complex, right? Moreover, the invariant basis property says that every maximal linearly independent set has the same size. And so that tells me that this simplicial complex is in fact pure. And it's a result of Stanley from 1977 that says that not only is it pure, but it's shellable. Right? And that's a very powerful result. In our example, our toy matrix example here, I have linearly independent columns 1 and 2, 1 and 3, 2 and 3, right? That simplicial complex is a 3-path. Oops, sorry. A triangle. And that's easy to show is shellable and pure, right? And then this term representable matroid. So a simplicial complex is a representable matroid if it's of the form Li of G. So if it's gotten by one of these linearly independent column sets for some matrix up to isomorphism, right? All right, back to the algebra. So if you give me a simplicial complex, then I can construct the Stanley-Riesner ideal, right? So this is the square-free monomial ideal in my polynomial ring that's generated by the non-faces of delta. Right? So I look at all of the square-free monomials that do not correspond to faces in my simplicial complex. So for instance, with this simplicial complex example that I'm carrying around of the three triangles, for instance, all of the variables correspond to my vertices. Those are faces, so those don't go into my ideal. A certain number of the edges are included in there, but some are not. So for instance, the edge 1, 4 is not included in my simplicial complex. So that gives me a quadratic generator. The edge 1, 5 is also not in there. The edge 2, 5 is also not in there. There are several triangles that are also not in there. So 1, 2, 3 is in there, but 1, 2, 4 is not. But that's a redundant generator being a multiple of 1, 4. So I get to throw that away. And it ends up, if you go through, then in fact, those are the 3 generators for that Stanley-Riesner ideal. Okay. Here are some facts. I said I was going to tie it together to Cohen-Macauliness and purity. So here we are. And I know that this is familiar to a lot of folks in the audience, but here I am. So the minimal prime decomposition of my square-free monomial ideal, my Stanley-Riesner ideal, is explicitly given by the facets, not the ideals generated by the facets, but the ideals generated by the complements of the facets, right? In particular, if my quotient by my Stanley-Riesner ideal is Cohen-Macaulay, that says that this ideal is unmixed. That tells me that the complements of the facets all have the same size. Therefore, the facets all have the same size. So my simplicial complex has to be pure, right? The converse here fails in general for the same reason that unmixedness doesn't imply Cohen-Macaulay in general. I'm interested in situations where the purity or the unmixedness does imply Cohen-Macaulayness. And a prime example of this is, for instance, edge ideals of trees. Right, so if you have an edge ideal of a tree, then unmixedness does imply Cohen-Macaulayness. And I like that because unmixedness is easier for me to verify than Cohen-Macaulayness sometimes. Right? Stanley gave another situation where, in some sense, purity implies Cohen-Macaulayness, and that's in the shellable situation, right? And this is really, for me, a case study in those long exact sequence arguments by induction that I mentioned before, the way that one proves that. In particular, if I start with a representable matroid, Stanley's 1977 result tells me that it's shellable, and therefore I get that those things are Cohen-Macaulay. Right. Now, the Stanley-Riesner ideals are part of the Stanley-Riesner correspondence. Oh, yes, before I get to the correspondence, again, the point. So my head gets, or at least it used to, it still does, I'm not gonna lie, get mixed up with all the complements and the non-faces and the complements and the decomposition and such. And Frank Moore was kind enough to explain to me the reason for that. And the reason is that by doing the complements, the non-faces, what it allows you to do is it allows you to see delta inside the quotient by the Stanley-Riesner ideal. Namely, if you look at the non-zero monomials, so the monomials that survive the quotienting process, those are precisely the faces of delta. And so you can see the simplicial complex explicitly in the algebra. The Stanley-Reisner correspondence says that this rule of assignment, where delta is assigned to its Stanley-Reisner ideal, gives a bijection between the set of simplicial complexes on my vertex at V and the square-free monomial ideals in that corresponding polynomial ring. In particular, the codeword ideal that I started talking about and then walked away from has to be a Stanley-Reisner ideal for some simplicial complex that I'll call delta of C. And it's a reasonable question to want to know, what is delta of C? And obviously, so I know the ideal, I know the decomposition, so I can write out what the facets are in terms of what I know the decomposition of the Stanley-Reisner ideal has to be, but I really want to understand it strictly in terms of the code, right? I want a one-step process instead of a multi-step process to understand what that simplicial complex is. The answer for that requires a tiny bit more coding theory. So it requires a notion of a parity check matrix. This is dual to the generator matrix for our code. To start, one considers the orthogonal complement of my code. This can be expressed in linear algebra by taking the null space of my generator matrix. And then because I want to consider code words, which are row vectors, I'm going to transpose all of those null space vectors. In other words, I want to look at all of the possible code words that dot with to be 0 with all of my code words, right? This ends up being, by the rank nullity theorem, an n minus k dimensional subspace. It's not it's not an orthogonal complement over a finite field in a nice way, like we think of over the complex numbers, but it is an n minus k dimensional subspace. So it itself is a linear code, and the coding theorists call this the dual code. And then a parity check matrix for my original code C is any generator matrix for the dual code. Okay, so I know this is a lot of symbols and stuff to carry around. I promise that there's a point coming in just a moment. So for instance, in my toy example over F2 with 2 spanning vectors, because I'm working over F2, the null space of my generator matrix is the null space is spanned by this code word 111. Okay. Or if you like, if you want to think about this in other characteristics, I could do 1 minus 1, 1. Right? And so my parity check matrix, in this case, that's n minus k is 3 minus 2, so one dimensional. So I'm only getting a row matrix for my parity check matrix. From the point of view of the algebra, here's the point, right? So I'm wondering, what is the simplicial complex that corresponds to the code word ideal in the Stanley-Reisner correspondence? And it is exactly that representable matroid that's gotten by looking at the linearly independent vectors, column vectors in my parity check matrix. And so in particular, my code word ideal can be gotten as the Stanley-Reisner ideal of the Li matroid of P, right? And so because, right, the Stanley-Reisner ideals of these representable matroids all are shellable, right? So sorry, this one's shellable tells me that this one's Cohen-Macaulay. And so I can read the depth straight off because depth equals dimension. So I've got depth k. And then the projective dimension by Auslander-Buchsbaum is exactly n minus k. So here we are again getting non-trivial algebraic information out of the code. Stanley goes further in 1977 by writing out what the Betty numbers for this Stanley Reasoner ideal or this codeword ideal. He's thinking in terms of matroids, right? He wasn't thinking in terms of codeword ideals, but you can obtain those by counting what are called flats in that representable matroid. Okay. And you can see in our toy example, there's my codeword ideal. The minimal resolution of that is a Hilbert-Birch resolution, which has length 2. And so projective dimension equals 2, the dimension of my code, the rank of my generator matrix as promised. And so again, to wave my arms enthusiastically about how you can get information about this codeword ideal from C, it wasn't obvious to us at all. So this codeword ideal was really, these information sets were described to me in terms of sort of a domination problem on certain bipartite graphs. That ended up not being precise. So it wasn't obvious at all that these things were unmixed, let alone that they were all Cohen-Macaulay, right? And so the next take-home point is just matroids, right? Because once you have this interpretation in terms of the parity check matrix, you start remembering all the talks that you heard people give talking about matroids, and it's like, I should go back and look at my notes for those because people know a lot about those things. Good. Excellent. A little bit more in the realm of niceness results for these. So Cohen-Macaulay is nice, shellable is nicer. What's even nicer is being vertex decomposable. And in fact, that was established by Proven and Vieira in 1980. That resolution, thinking of what we know about those Betty numbers. So so Anton, who's here, and Mohammadi in 2014 proved that that minimal free resolution is always cellular, right? These ideals are always Cohen-Macaulay. They don't have to be Gorenstein, right? And our toy example shows that I'm Cohen-Macaulay of type 2. And so another take-home point about these is that these codeword ideals are incredibly nice, right? But they're not too nice, right? So they're not all Gorenstein. So they have some extremely nice properties, but not necessarily being too nice as to be, say, overly restrictive. Recognizing that, of course, restrictive is in the eye of the beholder. So the last algebraic thing that I want to talk about is symbolic powers of codeword ideals. Now I'm interested for this particular project, staying in the realm of the square-free ideals. And so symbolic powers, of course, won't be square-free, but we can polarize them in order to get square-free monomial ideals. So this notation is one that I made up entirely. There may already be notation out there for this concept. I know it's one that people have studied in a lot of different contexts, but I'm simply taking the mth symbolic power of my monomial ideal and then the standard polarization of that. Okay. That will be a square-free monomial ideal in a much larger number of variables. If you sit down and write it out, for instance, in our toy example, this polarized symbolic power has 4 generators. I have the product of the variables, my original variables x, y, z, which for reasons I will write as capitals. And then I have 3 generators that correspond to the original generators. They are x, y, a, b, x, z, a, c, and y, z, b, c. And I'm using a very non-traditional list of variables for the polarization context. So let me write that out explicitly. So I'm in F, the join x, y, z. as versions of my original 3 variables, and then A, B, and C for the corresponding polarized variables. I get tired of writing subscripts really quickly, as you can tell. So writing them out this way. Joseph, once we realized how incredibly nice these ideals were, Joseph got bold and said, well, I mean, if they're so nice, are these polarizations of symbolic powers themselves code word ideals? They are unmixed. There are really nice descriptions of them in some contexts. And so asking whether or not this polarized symbolic power is itself a code word ideal for some code, which would necessarily be much longer than the original code that we had. The answer to that question, in fact, is no. So again, they're nice, but they're not that nice. And moreover, so we started by playing with the code word ideal for the symbolic square of my toy example. That's the one I just wrote out. That does not end up being a code word ideal over F2. For a while, I thought, for a minute, I thought that that had to do with the size of the field or the characteristic of the field. A lot of the things that happen around, can you build a code that does blah, depends on the size of the field, not necessarily the characteristic, but the size of the field. But this example, in fact, shows that that's not the case, because if you look at the ideal generated by those 4 monomials over any field, that in fact is not a code word ideal, regardless of the field. Okay, and I wanted to make sure and leave time for questions at the end, so I have a proof for that. It's really easy if folks want to see it, but we'll come back to it at the end if we have some time. Now, so that says that right, so this is a square-free monomial ideal. It's got a corresponding Stanley-Reisner simplicial complex. So that is not a representable matroid. However, it is a matroid, right? And so this slightly more general context of looking at these abstract properties of matroids, there really is value in doing that. I mean, yes, this is an easy thing to say, but in this context, right, I can still use the technology of general matroids in order to get information about those polarizations of symbolic powers. And I should say that so when I say it is matroidal, I'm not referring to all of the symbolic powers of an arbitrary code word ideal. I haven't checked that yet. That's on my to-do list. I'm talking about this particular ideal. Okay, so just want to be transparent about that. In the 1 minute that I have sort of remaining before opening up for questions, I want to point out that the information flow for me is really thinking about how does the information about the code give me information about the ideals? Because at the end of the day, I'm an algebraist. However, it's worth noting that the information does go the other way. So a result from 2013 of Johnson and Verdure says that you can actually use those Betty numbers, right, that Stanley computed back in the day in order to get information about what are called generalized Hamming weights of the code. Right, so the Hamming weight of the code is the size of the smallest support of a code word in your code. And the generalized Hamming weights are versions of that account for other things. And I'm not an expert in this area. And so you can look at the resolution and get information about the code from that, which I think is fascinating. And so at 1:51 Eastern time, I'll wind us up. This is my list of take-home points, which I won't repeat for you, and I'll just say thanks for coming.
Thanks so much, Keri.
You're welcome.
do we have any questions?
Oh.
Did you have a question, Claudia, or are you just in transit?
She's on the move. I
I have a
recognize this.
question.
Oh, great.
Who dat?
Hello?
Yes.
Hi.
Hi. You talked about how you can use the codes to give you information about the ideals, but can you
Yes.
go the other way? Can you get information about codes? Can you classify codes? Is there something you can do starting from the rings and the ideals?
Right. So that's
Um,
the slide here. That's giving you, right? So
Oh,
one
okay.
can compute the generalized Hamming weights for
Oh,
it.
got it. Okay.
That's one example of that. Thank you for the question.
Oh, sure. No, I find this really interesting. Thank you for the talk.
You're welcome. Thanks for the question.
Keri, and I also had a question. Maybe I'll jump in
Yeah.
while others think. On the slide with your potential proof you could offer us.
Uh-huh.
So you were saying you had this polarized symbolic power ideal. That's, yes, now it's coming from a non-representable matroid.
Uh-huh.
I know this is an example and you kind of said their general cases, something you're thinking about, but I'm wondering about the reason. Is the non-representability kind of the reason here that you're seeing this not as a code word ideal? And like what would your intuition be in general for kind of understanding the difference between code word ideals and like ideals coming from representable matroids?
Yeah, it's a good question, right? So the proof that this is not a code word ideal. I mean, I really do. So hypothetically, by way of contradiction, suppose that there were a code that did the thing, and then I manipulate the code in order to prove that can't be a code, right? So I don't actually refer to the matroid. And I like that because, right, I'm kind of getting information about a matroid by using the code instead of using the matroid to give me information about the code.
I see. So that doesn't exactly help you though in kind of understanding, or maybe it does. You're like using the code is telling you something that you need in the code to have the ideal correspond to something. But
Right.
does that give you some intuition then in general about how kind of ideals of that are candidates for code word ideals of this sort could or could not, like if they correspond to something representable, does it give you a way at least yet to distinguish between ones that do and don't?
So that do and don't what?
I guess I was thinking that correspond to codes or not. Like
Uh-huh.
you're saying, like
Right.
not all representable things that come from representable matroids are like, do you have enough information yet to find those?
Well, right. So the code word ideals are precisely the Stanley Reisner ideals of the representable matroids,
But
right? So, but knowing what happens with the symbolic powers, I'm not sure.
Okay.
I mean, once this toy example fails, I think that all bets are off. I mean, that you can't expect representable behavior from symbolic powers in general. I'm still hopeful about them being matroidal in general, but I don't have enough evidence to be able to make a hypothesis yet.
Thank you. That clarifies a lot. Thanks.
Okay.
Tim.
Tim.
Oh, great. Yes.
Thank you. I appreciate the talk, Keri, and I enjoyed it.
Thank you.
My question is in the theme of nice but not too nice. Are any of these code word ideals also pure? Like, do they have pure resolutions? Is that lurking in the background for some?
Oh,
You know,
I actually, the answer is sometimes, for sure, right? So for instance, the code word ideals that come from what are called MDS codes,
Okay.
So those are the ideals that are generated by all the square-free monomials of a fixed degree,
Yep. Mhm.
right? And so those resolutions have been constructed explicitly.
Right.
Is Anton still here? I
I
put
am.
Anton on the spot. Do you know the answer to that question, Anton?
The
Since
question
you
is just when of
literally,
these have pure resolutions?
yeah.
Yeah, maybe I should know that. I don't know off the top of my head. But you're saying
Yeah.
if they're generated in fixed degree, they will? Is that?
If they have all the square-free
Generated.
monomials of a fixed degree, then they are. And that can be, that resolution's given in terms of hook partitions,
Mhm.
and they're linear. So,
Yeah.
but in general, I don't know. I
Okay.
would want to look at, I need to spend some time with the proof that they're cellular, because I think that's a mapping cone argument. Is that right, Anton?
Yeah, that's right. So it's hard to maybe
Well,
detect.
but if you're inducting somehow, then, you know, all you have to do is understand that chain map, right? How hard could that be?
Yeah, you keep adding, you sort of cone on these Coates-Hul complexes, and so
Right.
tell you that.
Yeah.
Been a little
I
while.
have other questions that I'm interested in about the resolution as well, Tim, right? So from my homological life, I'm really interested in whether those resolutions have DG algebra structures.
Mhm. Sure.
And so I think that there's lots of questions about these that have yet to be resolved. But thanks for the question. Alex?
Hi. Sorry, did you mean me or?
I did.
Okay, thanks. That was a great talk. Thank you very much.
Thank you.
I have a somewhat naive question and then a more open-ended question. The naive question is, you said that the information sets of C are independent of the choice of generator matrix. Is that something that is sort of obvious from some linear algebra concern, or does that require a little bit of proof?
No, because you're using you're using row operations in order to go from one generator matrix to another.
Oh,
And
yeah.
so you're preserving the linear dependence and linear independence relations in those.
Okay.
Good question, though.
It seemed like something that.
It's obvious when you think about it the right way, right?
Yeah.
If you just think about it in terms of substitutions, then it's not obvious at all.
Yeah. And I guess that's sort of where my open-ended question is. You were talking about linear codes, and in my life, I spend a lot of time thinking about more or less random binary codes. And so I was wondering how much do you learn about a code when you don't know that it's a linear subspace? Right.
Oh.
Right. That's the open-ended question.
Yeah, I don't know what to do if it's not linear. So most of my time I'm thinking about binary linear codes. But if you take away linearity from me, I don't know what to do.
Okay. And is the linearity baked into some of the proofs in here, or is it just like?
Yeah, because so much of it hinges on the generator matrix and the parity check matrix. And if you're not linear, then you just don't have those tools.
Right. Okay. Yeah.
Right. I mean, you could still if you just give me a code, you can write down a codeword ideal, just throw in all those monomials, but, no reason to suspect that it's, matroidal
Right.
or anything. So I would have to think about that.
All right. Well, you're going to the sectional in DC in a month, right?
Yeah.
All right. Well, hopefully I'll tell you something then.
Okay, cool.
All right.
Thanks for the question.
All right, well, I don't see any more questions right now. So in the interest of time, I think we should thank Keri one more time for a wonderful talk. Thank you so much.
Thanks a lot for being here, everyone.
Yeah, thanks for coming.